So, good morning, everybody. Welcome to the 13th edition of the Code of the Month. Today we have the pleasure to have as guest Stefano Markidis from KTH. Stefano is the coordinator of Plasma-PEPSC CoE, and they are developing 4 codes for simulation of plasma, and eager to learn about that. So the floor is yours, Stefano.
Thank you very much, and good morning, everybody. As has been said, this will be the codes plural of the month. Since I'm going to give a brief overview of the 4 codes that we are working on in the Plasma-PEPSC Center of Excellence. So a brief overview of my talk. I will just give as a starting point some background about what is a plasma, what is a plasma simulation, and why plasma simulation are complex and difficult and require Exascale machine. I will just give a little bit of motivation, and then most of my talk we will revolve around these 4 codes. I will explain what are the features of these 4 codes, what is scalability, the work that we are doing, and the next step. So let's start with the first part of my talk. What is actually a plasma? A plasma is ionized gas. It means that the electrons are free to move, are not in the atom, but are mix-ups with the protons. In order to have ionization, you need to provide to the system high energy for the electrons to pop up for the electrons. So typically plasma are associated with high energy states. So you need some ionization energy to make electrons pop up from the atoms. Because plasma consists of electrons and protons all mix-ups, so these are charged particles, and when they move, they're capable of conducting electricity. So when they move, they can create a magnetic field. So whenever you have a current, you can create a magnetic field around it. Also an electric field. If you have a separation of a charge, you will have some electric field that try to neutralize again the system. So not only the dynamics of these electrons and protons are capable of generating electric field and magnetic field, but also their dynamics is driven by the electric field and the magnetic field. Particularly, if you have charged particles, there will be acceleration that is due to the presence of electric field, and then will be a rotation due to the Lorentz force if there is a presence of a magnetic field. So this has a very interesting situation, and this self-feedback mechanism that plasma itself is capable of creating electric field and magnetic field, but the dynamics also of the plasma is determined by this electric field and the magnetic field. So this introduces like a nonlinear interaction and the nonlinear dynamics in the plasma. So differently from grass, plasma are capable of supporting collective behavior. What does it mean? It means that the plasma, and because of its nature and its coupling with the electromagnetic field, is capable of supporting a wide range of waves that can propagate from local to global, so affecting all the system, and also is characterized by a large number of instabilities that convert, for instance, magnetic field energy into kinetic energy, and vice versa. So most of these waves and instabilities affect the dynamics, and particularly, for instance, in fusion system where we have a plasma, instability are obstacling the confinement of the plasma in a smaller place. So probably if you've heard the terms plasma the first time, is what you need to know that the plasma is considered fourth matter of the universe, and is basically omnipresent in the universe itself. So the sun itself, you see these arches. This is plasma. The plasma is the mechanism for creating fusion energy in the first fusion device that we're using. Also, they're widely used in accelerator technologies, for instance, for creating beams through the interaction with the lasers. So why is important? As I said, you can find the plasma everywhere in the universe. So if you want to know, if you work on astrophysics and working on the universe, you need to deal with the plasma system. Most important for us in society is a key for fusion energy. We need to create first plasma, then heat it up, be in a position of having fusion energy in a confined environment. Is also a key for advancing materials processing, for instance, for the chip production, for the etching. We use plasma, and it's extremely important also for medical application. For instance, for cancer treatment, there's possibility of using beams to kill cancerous cells. Is extremely important if you're working on space, astrophysics, and particularly protecting the assets, human assets in space. You need to have predictive capabilities of what is the plasma behavior in the space, what is connection with the sun. And a lot of plasma propulsion technologies is actually based on using plasma. The plasma is ejected by plasma thruster, so that can we navigate through the plasma. So why we need Exascale system? Why the plasma simulation is so difficult? Well, the first motivation is really the complexity of the plasma behavior. As I said in the second slide, is the plasma behaves like a complex system and show a complex behavior. This is due to the fact that the plasma itself generates some fields, and the plasma is also being to the same fields that is creating. So it's a self-feeding mechanism that is highly nonlinear. So you need a nonlinear theory to take care of handling the modeling of such a complex behavior. It turns out also to provide the most accurate solution to the modeling problem. Also, we need to go to the most detailed description of the plasma itself. The very higher level description, you can think of the plasma as a fluid, and this is and this works in some cases, but for the problem that we want to solve in Plasma-PEPSC, this is very raw and crude approximation. So we look at and we use much more detail, and that are called kinetic models that are looking at solving the evolution of the distribution function for the electrons and the protons. This is much more difficult problem than treating the plasma as a fluid. So we need also to have a much more detailed description of the plasma in order to describe accurately the phenomena that are important for in this system, for instance, fusion energy. Another important problem that is obstacle, the simulation that makes simulation very difficult is the multi-scale nature of the plasma system, and this is due to the fact that the electron mass is much smaller than the proton's mass. 1,836 times lower. So you can think that you can already imagine that electrons are relatively very, very small in mass when compared to electrons. So they are free to move very, very, very quickly. The protons are much more massive, so they move way, way slower. So from a numerical point of view, you need to follow the dynamics of the electrons, but still you're very much interested also to follow the slow dynamics of the protons themselves. So you need to resolve frequency of typically of the electrons that are very, very fast, but you are more interested in the global behavior of the system that is determined by the motion of the massive protons. That's one problem. So the disparity of electrons and the proton mass that give this multi-scale nature. The other major issue is that there are some phenomena that are very localized in space. So there's a phenomenon, for instance, called magnetic reconnection that it occurs in very, very small part of the system. It might be a fusion system, it might be a space system, it might be astrophysical system. But these phenomena that originate on a very small scale, it then propagates and affects the whole system, typically hindering, for instance, the confinement, infusion, or determining a solar storm. So phenomena that are born very local, very, very small, they're capable to affect the whole global scheme. So we want to model all the global, but still we need to make sure that we can capture the birth of these phenomena at a very small scale. So these require a high computational cost. As I said, we use very advanced technique called a kinetic technique that aims at modeling the overall evolution of the distribution function. This often translates to, for instance, to sample the distribution function with the computational particles and follow the trajectory of all these computational particles. Often we are talking about millions of computational particles. We need to follow through the global system. Together with that, then we need to solve the electromagnetic field, and this is also a major cost when it comes to the computational cost of a plasma simulation. Also, there is a validation and verification part that is extremely important. So all the tools that I'm showing here are used for predicting behavior of plasma in technological system. It might be in the tokamak, in the fusion device. So then compare to experiments. It might be beam creation, laser plasma interaction for creating accelerator that are actually produced in the labs, and then we use simulation to compare and also help the design of this system. We use plasma simulation for a plasma material interaction from plasma wall interaction, for which we have a data and we validate. So there is a very important step to validate and verify the correct functioning of the models that we're using, of the code that we're using. And this is a mechanism that requires a lot of time, a lot of expertise. And last but not least, plasma simulation today, it requires a wide range of interdisciplinary collaboration, going from computer science, high performance computing, parallel computing, computational plasma physics, including modeling technique. It requires knowledge, advanced knowledge of plasma physics, and also knowledge on how to verify and validate. So this is a huge team that requires a very diverse kind of background. So very happy to have them in the Plasma-PEPSC. So the Plasma-PEPSC is the Center of Excellence that is focusing on simulation for plasma. And the main key goal of the project is to make the codes that we have in Plasma-PEPSC exascale. So the project is driven by science question, what we call the grand challenges, and we aim to solve these grand challenges in the plasma science with exascale computing. We have 4 codes that I'm going to describe you quickly in the continuation of my presentation that address key plasma science. And so we have the very ambitious goal by the end of the project to make a key advancement in understanding and addressing the grand challenges. And the first main grand challenge is about fusion energy, and we have 2 codes. One is called GENE, another that is more focusing on material plasma interaction is called BIT1. We have a grand challenges related to modeling at a very high accuracy, a novel plasma accelerator, and the code in this case is PIConGPU. And then we're also looking at the modeling of Earth magnetosphere, so the interaction with the solar wind. So we have a use case related to space physics and space weather at large using the Vlasiator call. As I said, we have 4 codes. The preparation and optimization of these 4 codes in the Center of Excellence are driven by solving these plasma physics grand challenges. So we are monitoring what is the advancement with the figure of merits in each of these 4 grand challenges. In the continuation of this presentation, I'm going to give you a very brief overview of the 4 codes. I will first present you a video just detailing, just give you a visual understanding of the 4 codes and the technique. The first code is PIConGPU is a particle in cell. That means that what we are doing, we are sampling the distribution function of electrons and the protons using computational particles. And you see here like a sample in these videos of the computational particle themselves. In this case, it is interaction of a laser with the plasma that creates beams. So these are extremely computationally intensive simulation that require accelerator. I also want to showcase here, some advanced data analysis and the in situ data technology that you see here. So many of the results you see here actually you can get at the runtime using some in situ visualization data analysis technology. That was PIConGPU, particle in cell. And the second major code we are working on is the Vlasiator code. This is a hybrid. It means that is hybrid code. It means that the protons themselves are modeled as let me see if I can go back to the. To go back to the Vlasiator part, this is a little bit tricky. So this is again the PIC with the PIC on GPU. As I said, they create they have a computational particles, and we model the interaction of electromagnetic field with these computational particles. Particularly, I want to to showcase both these are huge simulation, but also the integrated data analysis tools that we say here to understand the particle distribution and the behavior, and provide insights for the scientists about the science itself. As I started before, the second important application is Vlasiator, that is modeling the magnetosphere. So in this case, on the right side, you have solar wind that is pushing the magnetic field in one part, and then is elongating on the other part. The code, as I said, is Vlasiator, is hybrid technique. And the second, the third code is called Gene, and is a code that has been designed for simulating plasma behavior, in particular plasma turbulence within the tokamak. So you see this big donut. This code using so-called gyrokinetic approach is still kinetic, and so we are often modeling at a very high accuracy the distribution function, and but introducing an approximation that is very valid in the presence of very strong magnetic field in the tokamak that is called gyrokinetic. Last on the list, we have bit one, and that is a particle in cell code, still simulating the distribution function using computational particles, completely that is designed for plasma material interaction. I will now go through a brief description about the particular features of the four codes. So I will provide you more detail after I gave you more visual understanding of their functioning, and I will give more like a computer science aspect. So I will skip more the physics and the science part and focus on what are the advancement, what are the characteristics of the codes in the Plasma-PEPSC Center of Excellence. So the first code is PIConGPU, is explicit particle cell, very advanced with many different features, for instance, radiation, relativistic treatment of the system. As I mentioned in the previous video, this main system is applied to our laser plasma interaction. For instance, laser wake field acceleration, laser solid interaction is largely used in relativistic plasma, and also for modeling high energy physics that includes plasma. As the names said, the main feature is extremely high performance on the GPU. So this is highly optimized for graphics processing units, and this is a unique case where the code was first designed with the GPU in case and then ported to the CPU. So this is extremely interesting code. So today is not only GPU. In reality, it supports a very wide range of different architecture, and is doing that by using a framework called Alpaca that allows for extremely portable, but also extremely performance portable porting of PIConGPU to many different architecture. And is a relativistic framework, so it's a relativistic PIC and designed for relativistic plasma, accurately capturing high energy particle dynamics They also use extremely high accurate scheme when it comes to the numerical parts. So is written in C++, but the main porting layer for the GPU, CPU, and all the new computer architecture is done by using Alpaca. The performance of PIConGPU on very large scale system is outstanding. In fact, it was a Gordon Bell finalist in 2023, and we are very much happy to have in the main developer, who are the Helmholtz Centrum in Dresden and Rossendorf at HZDR with the PI, Professor Michael Bussmann. We're very happy to have them in Plasma-PEPSC because they provide is a point of reference for all the codes, how to improve portability, GPU porting, and also explore many of these tools that the Dresden group has been supporting and developing. The scalability, as I said, is really impressive. This is just a small one, but the PIConGPU has been testing on a wide range of different systems with a very high scalability. Here is just an example of looming strong scaling that is very difficult to achieve, increasing the number of GPUs. And on scaling, and so this is strong scaling, and you see that the scaling is basically perfect, right? So that increasing the number of GPU and showing that this is the ideal code to scale up and to efficiently use very large scale GPU system. I just also want to say a few brief words about other technologies that the PIConGPU team, the Helmholtz Center, Dresden, Rossendorf, is also bringing to the Center of Excellence. And I think we are already seeing, some of the collaboration, looking at more at programming side, portability of the other codes to GPU or to very large scale GPU system. So the Dresden group also is the main developer, also bringing into the Center of Excellence the Alpaca portability layer. So this is a library that facilitate and I would say accelerate the accelerator development with rather minimal dependencies. So this is the way that PIConGPU provides extreme platform independence without actually changing the code. So that rely on Alpaca is so it supports all different kind of GPU, NVIDIA, AMD, and Intel GPU, but also new CPU, new architecture, ranging for traditional x86 ARM. We are doing RISC-V in the project, and also IBM Power. They provide a unified kernel implementation. Does it mean? Well, in few words, it means that you just write the kernel that you're after only once, and then you don't need to rewrite code specifically in CUDA, heap, or OpenMP. So the Alpaca will take care of it. The abstraction layer is very similar to CUDA, and OpenCL provides abstraction of grids, and threads, and blocks that is very similar to CUDA, and also they provide mechanisms to interact with GPU shared memory and typical synchronization part. And as I said, the very strength of Alpaca. You just write once your code, your kernel, and then you support a wide range of different backends from CUDA, heap, and SQL for the three different kind of a GPU architecture from 3 different vendors, but also for CPU part, they provide task-based backends for the CPU to increase the utilization. And another exciting initiative that HCDR brought it to the Center of Excellence is OpenPMD. So this is more related to the I/O part that we believe that is an Exascale challenge. You know, how to move, how to do this efficiently. So SDR included in in OpenPMD into the Center of Excellence. OpenPMD is an international effort. SDR is one of the promoter, but is widely supported now and by different organizations all around in the world. But this is something that we start using in Plasma-PEPSC to both to organize data, so that is fair data, but also to largely improve the performance of the I/O system and the I/O of the particle simulation. In a nutshell, is a standard. So there's a document. If you go to the website for metadata and naming schemes, it was born for particles and mesh data, and specifically for how we can share simulation data, both experiments, and this will close the gap. How we share the data between simulation and experimental community. So the OpenPMD is one of the main focus when we are looking at the data. So this is both minimal data, but also can be used as a library itself. There's an API that can be used to improve your code. So there are different support data formats: ADIOS, HDF5, BTK, XML, NetCDF format. So it's some support compressed format or format that you have used in your code, and it provides also the possibility of implementing parallel I/O in a very easy way. So that was the first code. PIConGPU specialized in GPU, very extreme scalability on very large system. The second code is a Vlasiator code that is developed by University of Helsinki in Finland, and there's a huge team around that, but the PI is Minna Palmont. So this is a code that is mainly designed for studying space plasma. That means magnetosphere, dipole interaction with winds. So it can be the Earth magnetosphere with the solar wind. So it's dedicated to studying magnetospheric physics, solar wind applying interaction, but in general all the geospace and environment. So this can go from modeling small part to global part. But I would say the very strength is to model the global part. It uses a hybrid technique where the protons themselves, often called the ions in the plasma physics community, are modeling the evolution of the distribution function. So instead of using particle, in this case, we are using the discretization of the hybrid-Vlasov equation that is describing the evolution of distribution function. And the electrons are described not as with the distribution function, but more like a fluid. So this is as an approximation in order to be able to average across some small scale of the electrons and attack the big problem of the global simulation. So the main feature, the uniqueness and the beauty of this code is really the capability of modeling global simulations, so can simulate large-scale space environments such as the Earth magnetosphere. So there are a number of algorithmic advancement that makes this code extremely interesting that you see here in this very nice plot made by the Vlasiator team. And you see here different algorithmic improving over the year, and you see some step. So as we know, whenever we have a major algorithmic improvement, we have a major performance in improvement in the code. So we go from the initial one. So we have the velocity distribution function, VDF in short. So the first major algorithmic improvement was going from a dense description to a sparse description. So using sparsity of the distribution function to improve memory management and make this simulation feasible on a large scale. Then semi-Lagrangian Vlasov solver. I would say one of the most exciting part is really the adaptive mesh refinement. That is very exciting and as a critical technology when you do space simulation. For instance, you want to have a very refined grid close to the bow shock, or any area of the space where there are very strong gradient. So you want to have very small cell in that area. And then you might want to have a coarse grid where there is not much change in the dynamic of the plasma. So you want to mix up, very small grid with some grid cells with other smaller, depending on the physics of your system. So this is a true major advancement in general for all the space simulation. However, this come up with the issue that suddenly you have a part of your code, or part of the processes of your code, they have a lot of work to do because they have many grid cells or very small, and other one they have a very little to do it. So these then require load balancing technique, and that is also extremely advanced technique in order to assign the job, or to make the job in different processes that is equal, so that the simulation doesn't need to wait for one MPI process just idling. So this is one of the major challenges, more the computational challenges, how to implement some load balancing that are scalable, that are capable of using Exascale systems. The Vlasiator team last year is doing major advancement in this part. The other major advancement that we are working in Plasma-PEPSC is really the GPU part. There's quite a lot of work on handling GPU. Also, the GPU in this case are mostly related on how to deal with the VDF, how to have specific data layout on the GPU that's still high performance. For instance, you might want to use a hash map for this data structure, for data structure for the VDF. So this is a very intriguing, very exciting work that the Vlasiator team is doing. Together with this exciting project, the very first step was to produce an analysis. You see how quite a detailed analysis of the Vlasiator code, giving also an idea of the complexity of the code too. We try to understand, where potential bottleneck on the code and try to optimize. So here an analysis of communication topology. So these are typically 5D or 6D simulations. So you might have communication along 5 direction, and you see here the communication pattern where you have MPI ranks on the x-axis, MPI ranks. So this is a plot on who is communicated to who. And also we look at the more in detail of at the issues on the MPI part here. The scaling, so also we perform a number of scaling. So here is Lumi C, or using a 5D Vlasiator, strong scaling on the CPU partition, 100, 200, 300. You see here around 300. Start flattening a little bit. So we are looking at at the cause, root cause for this. We identify, for instance, the part about the communication part and communication, how to aggregate the units and decrease the communication part. And the Vlasiator team is doing a great job in this direction. So after Vlasiator, we move now to two codes that are relevant to the fusion one. The first one is going under the name of Gene and GeneX in general to the Gene family, a set of simulation tools based on gyrokinetic Vlasov. It might change the numerical scheme, but the basic technique is so-called gyrokinetic. So this is a model that is extremely powerful whenever the magnetic field is relatively strong. It means that instead of following all the rotation of the electrons, we can just follow the center of the rotation. So we remove this high frequency from the system by just averaging around this rotation, but has all these other similarity to the other code in the sense that it's still kinetic, so it's still having the same challenge of the other code. As I said, is used for fusion, in particular for IMF, so magnetic confinement fusion, and there's been extremely impactful work, scientific work by the Max Planck Institute, the IPP, Plasma Physics Group, on the plasma turbulence. So this is very impactful work in trying to understand plasma turbulence. Obviously impacts the confinement and the dynamics of the plasma. So to unlock the nature of plasma turbulence in the core region of the document is a major step forward. So major physics achievement here. So these are high fidelity turbulence simulation. They have a very advanced physics models, and one thing that we are working on Plasma-PEPSC is really to improve and increase, to understand first the difficulty, but also improve the GPU porting, increase the large the scalability at extreme scale, but also looking at how far we can go when it comes to employ mixed precision in the algorithm itself. The community itself always use double precision, but there is a lot of work by a developer team of Gene in assessing the goodness or how bad it is, the mixed precision and the compression. Also, this is it is a work that potentially can change all the future of plasma simulation, because if you are capable of using this, we are able to have higher, way higher computation efficiency. So this is something that has been very exciting. As I said, the main developers is Max Planck Institute for Plasma Physics, so PIConGPU, but also with the participation of the Max Planck Data Facility Computing with Professor Irving Laura supporting all the computer science part, and Tilma Deitmar who is the scientific coordinator of our project. As we did for the old code, we perform a performance characterization of all the codes, and here we have a snapshot of the profiling of the gene. We try to understand both, which part is taking the most. So here, for instance, you see a snapshot of all the function in the case of gene X. Memory usage, and as I said, also a lot of work on the I/O part itself. We have different scaling. I just want to showcase one. We have a gene X scaling, a number of different architecture. This is a weak scaling, so it means that if you increase the number of CPU or GPU, should be a flat line in the real case. So anything up show a little bit inefficiency when increasing the number of resources. It's not inefficiency. This is just the results of additional communication that you have. So you see that so the higher bar here, so on the y-axis there's execution times, and then here's the scale. You see that in terms of CPU, the scaling is actually quite good. You can see roughly 80% of efficiency. One thing that I want to highlight is actually the small bar here that is actually use of the GPU. Right? So you can actually also see the enabling technology of GPU, how what is the improvement that we can reach. So this is a current area of research. So the gene and GeneX team are pushing forward for, as I said, a lot of work on the data management, compression, mixed precision to see how far we can go. Also, a lot of work on the GPU side. See how these enabling technologies can improve fusion technology. I will now finish up with the last code that is a bit one. This is a fantastic and unique code. Is electrostatic particle in cell PIC code. So this is we discretize, we sample the distribution function with the particle, and we follow their trajectory. The beautiful part of this code is this part here. It makes extremely unique. It's using modeling at the atomic processes, collision, and interaction with wall at very high accuracy. So this is a super unique code. So it's electrostatic code with the collision model. It provides a very high accurate description of a plasma material interaction. It's mostly used for a plasma wall interaction, so the Tokamak infusion device. And the main feature are these direct simulation Monte Carlo methods to accurately model nonlinear interaction between plasma, some neutrals and impurities with different models for collision. So it has a very wide and comprehensive collision models, a wide range of elastic and elastic collision. It has a very detailed plasma wall interaction models, and then use extensive atomic and plasma wall interaction data. So that is extremely unique and also extremely beautiful feature of the code. So we're very happy to have them. The code is in C, using minimum number of libraries, mainly NPI. As a part of the project, also we start looking at supporting OpenMP and OpenMCC, and we have the initial support. And as the work is led by the Czech Academy of Science and Plasma Physics, Institute of Plasma Physics, Czech Academy of Science. with a PI, Professor David Chikaya, and with also major work, but from the University of Ljubljana with the Professor Leon Kos. He also would work with our project manager from QTH, Jeremy Williams, that has been instrumental to do a lot of work I'm showing here. As other code, we provide performance analysis. We identified what part of the codes are the most difficult. We analyze issues with load balancing, checking which MPI process is doing more. We studied accurately what is the communication partner, and as I said, we did initial GPU porting using OpenMP and OpenEC. You see here some results. So these are just the initial results. They look promising. We understand where we want to go, and we will push forward for it. This is an example also of bit1 strong scaling. So you see, for instance, there are two test cases. One is ionization. The second one is shed. The ionization is too small problem. So this is the blue line. So you see it start scaling, but then the problem itself is too small to scale more than 2,500. In much more realistic case, you see also the very good scaling in the shed project up to 20,000 and also beyond. So very happy with the scalability part. I want to just showcase one of this cross-fertilization work. I said that as the group from Dresden introduced to the Center of Excellence OpenPMD, and also now today we have support on OpenPMD in bit1. Thanks for the collaboration, not only of the key people in bit1, but also with the key people in the PIConGPU. I just want to give you here an example of the transformative power of, for instance, OpenPMD. On the y-axis, we have the the bandwidth, so the throughput, in gigabyte per second. So the higher is the better, and then we have the different number of processes on the y-axis. And there are two columns. The blue ones are the original I/O in bit1, and this is the results of using OpenPMD in bit1. So you see that we are going from roughly 1 to 10 or so. We are basically obtaining two orders of performance in improvement. So this is just to showcase how also important it is to have different codes of the same community. For instance, both are PIC, and some of the code already using technology can provide the expertise and skills to deploy. For instance, in this case, OpenPMD in the code itself. Similarly, we also noticing the same things for that pattern. I just want to say a few words. Also, we have an extremely exciting work on so-called co-design and on working with the code on a simulator and the first prototype of the Cyper ARM processor. So this is a simulator and the EPAC RISC-V accelerator. And so in this case, so the expert from BSC, Fort, and Cyper have access to the code, is testing the code on the simulators, providing feedback on how to change the code in order to use the system. And I just want to finish up with this and take a few questions. The overall goal is to make so this code are all public. So we are. Please contact me, contact us at Plasma-PEPSC if you see that you want to use on a code, you want to know more about the capabilities of the code. On these slides, I'm done. Thank you very much.
Thanks a lot, Stefano, for this very comprehensive and detailed overview of your codes. And I think we have time for very few and short questions. So the floor is open for questions. I'd like to thank you again and thanks the audience again. And just a hint, we will have a next talk of the code of the month in a bit less than 3 weeks, I think, on the 19th of February already. So thanks a lot for bringing us insight into your plasma simulations, Stefano.
Thank you. Thank you very much. Bye-bye.
Thank you. Bye-bye, everyone.
Bye.